Our second big rule or law is the addition rule. The addition rule is really simple. It says the probability of A union B, and again, that's not really a U, that's a character thingy. Probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. This is, in our minds, the word or. So what we're saying is, what's the probability that Federer or Nadal will win the U.S. Open? Well, the answer would be the probability of Federer plus the probability of Nadal minus the probability of both of them, which is 0. So this rule is a rule about or. What's the probability that the Vikings or the Packers will win the Super Bowl? What's the probability that I'll win at craps or win at poker? Even though I don't play either one. It's the addition rule problem. So let's suppose that 50% of students go to the student union on Tuesdays, 40% of students go to the library on Tuesdays, and 20% both. What percentage do at least one? Student union or library? Well, the answer is probably student union, union library. And I know that sounds funny. Student union, union library equals probably a student union plus probably a library minus the probably a student union intersect library. So that's 50 plus 40 minus 20 is 70. Nice and easy math, yes? Just took the numbers from the last slide, stuck them in an equation, got 70%. We can also do this on something called a Venn diagram. A Venn diagram means we consider this box here. We draw a box. That box is everybody. Then we put a circle in for all of the people who go to the student union, and we have a circle for the people who go to the library, and we make sure that those two circles overlap here in the middle, and the part where they overlap is the students who go both places. So we can divide this up. This is 50% of students who go to the union, but 20% of them go to the library, so that means 30% go to the union but not the library, and 20% go to the union and the library. And we have 40% who go to the library, since 20% of them also go to the union. We have this 20% in the middle, which is both the union and the library, and then 20%, which is just the library. These people, if we just added up the 50 and the 40, we'd count these students twice because they go both places. So we have 30% who go to the union and not the library, 20% who go to both, and 20% who just go to the library. So 30 plus 20 plus 20 equals 70, which is the same as taking 50 plus 40 minus 20 and getting the 70. Cute little diagram here, the Venn diagram. We have the multiplication law, which is the probability of A intersect B. That's an AND rule. So when it's an AND problem, we're going to use the multiplication rule. So what's the probability of me being late to class and me not having my lecture with me? Well, probability of A intersect B equals the probability of A times the probability of B given A. If I am not late to class, or if I am late to class, it may affect whether or not I bring my lecture with me. Maybe I'm hurrying out of the house, and so I was late to class, and because I was running late, I forgot to put my drive in my pocket. So what's the probability of rolling 2 6s in a dice game? Well, each dice, the probability of A is the probability of rolling first 6, and the probability of B given A is the probability of rolling second 6. Since those two are independent events, since they don't affect each other, they're both 1/6, and the probability of A intersect B, 1/6 times 1/6 is 1/36. So the chance of rolling 2 6s, or alternatively, the chance of rolling a 12, if you're rolling a pair of dice, is 1 chance in 36. Now here's another example. We have a bowl. That's a bowl down there. You can tell, obviously, it's a bowl, and in that bowl there are 7 M&Ms. And 4 of those M&Ms are red, and 3 of those M&Ms are blue. If I'm going to pick M&Ms at random, what's the chance that I get 2 red ones? Well, the first time I dip in the bowl, there's 7 M&Ms in the bowl. 4 of them are red, So there's 4 chances in 7 of that first time. But once I pull that M&M out of there, now there's not 4 and there's not 7 anymore. So the first M&M, 4 out of 7. Now there's 3 reds and 3 blues. So the probability of B, a red M&M, given that I already got a red M&M, is 3 out of a total of 6. So the probability of getting 2 red M&Ms is 4 out of 7 times 3 out of 6. The probability of A intersect B is 12 chances in 42. Okay. What's the difference between the 2 examples? Well, the first time they're independent events and the second time they're not. So if they're independent events, it's really easy. We don't care about the given A part, but the second time when they're not independent events, we care. So if the probability of A given B equals the probability of B, then those are independent events. If we play dice, you roll a pair of dice, they're independent events. If we're dumb enough to play Keno at the hotel, no. Keno is a bunch of numbers that can each show up one time. So if 20 has already shown up, 20 can't show up again. If there's 80 ping pong balls in the bucket that they're pulling out of, the chance of getting the 80, if you want to get the number 20, chance of getting 20 on the first pull is 1 in 80. But now there's a ball gone. There's only 79 balls left. So the chance of getting it on the second try is 1 in 79. Keeps changing, not independent. And again, when you play cards, those are not independent events because every time you take a king out of the deck, that's 1 fewer king, and the probability of getting a king goes down. Okay? So the probability of A intersect B is probably A times probably B for independent events. Simplifies our rule a little, but otherwise we have to adjust for that given A part. There's also a law that we call the Elimination Law. It doesn't make any sense to call that, but that's what we call it. And that just is math. Just says if we got to use both laws to solve a problem, you do the multiplication rule first. It's just like algebra. It's a simple rule of algebra. What's that mean? Well, the answer is that we show these multiplication problems on what's called a probability tree. So what we're going to do is draw a set of branches on a tree to represent our problem. Each set of branches is going to have a probability of 1, and the whole tree together is going to have a probability of 1. It's like magical. So we start and we draw a box. We want to roll 2 6s. So the first roll of the dice, each box represents a roll of a dice, a roll of a die. I can either get not a 6 or a 6. So I roll my die. I can get a 1, 2, 3, 4, 5, or 6. But I'm only interested in the 6. So I have 6 going this way and didn't roll a 6 going that way. And again, I want to roll 2 6s, so I don't care what else I rolled. I'm either going to roll a 6 or not a 6. Given that I didn't roll a 6 the first time, and I rolled a second time, I can either get a 6 on the second one or not a 6 on the second one. And again, given that I already rolled a 6, I roll again, and I can either get a not a 6 or another 6. And this is the branch I want to take. I want to come down this branch and then come down that branch, and the other branches don't win for me. This problem. So what's the probabilities? Well, the probability of rolling a 6 is 1 in 6, so the probability of rolling a not a 6 is a 5 in 6. So this set of branches have a 1 in 6 and 5 in 6, it adds up to 1. This set of branches has a 1 in 6 and a 5 in 6, it adds up to 1. And this set of branches has a 1 in 6 and a 5 in 6, and it adds up to 1. Now, we're going to use the multiplication rule, which means we're going to multiply down the lines, and we're going to get a probability that's associated with each of the 4 lines. Okay? So this line would be not a 6 and not a 6, yes? This line, I didn't roll a 6, but then I rolled a 6. And don't ask me why that just happened. This line is 6 and no 6. And then this last line down here is 2 6s. Okay? So let's do a little math. The top set of branches up there is 5 6 times 5 6 is 25 out of 36. 5 out of 6 times 5 out of 6 is 25 out of 36. That's not a 6 and not a 6. The second set of branches is not a 6 and a 6. And we multiply that out and we get 5 out of 36. The second line is a 6 and a not a 6. And that's 5 out of 36. And then the last line is 6 and 6. And you notice that we add all those up, we get 36 over 36, which is equal to 1. So again, 25 out of 36, 5 out of 36, 5 out of 36, 1 out of 36. And it all adds up to 1. We have all these ones in here and a big one right there. Okay, so do the 4 M&Ms red and blue problem. Can we do that? We start out with a box. We pull out an M&M. It could be red or it could be blue. And then we reach back into the bowl and get a second M&M. And the second M&M could be red or it could be blue. And here we have second M&M down here, and it also could be red and it could be blue. So let's figure this out. There's 7 M&Ms here. 4 out of 7 and 3 out of 7. If I get a red one already, there's 3 reds out of 6, and there's 3 blues left out of 6. If I get a blue one on the first try, there's 4 red left out of 6, and 2 blue left out of 6. Notice those add up to 1, those add up to 1, and those add up to 1. And these sets of branches are different because this example is not independent events. The last example is independent events. This example is not. So now we just multiply down the line. We get 12 out of 42, which is what we calculated before. We also get 12 out of 42. Strangely enough, we get 12 out of 42. And then we get 6 out of 42. And if we add those up, they add up to 1. They add up to 42 over 42. Okay, good. So what are we going to do now? We're going to go practice.